Well, friends and Mertonians, and some of you overlap in both of those places, welcome to the Ockham lecture. Tonight we are going to go on a journey to the very early universe with Charlotte Mason. Charlotte herself was always clearly going to be destined for the stars. We knew this even before she arrived here in Merton. I think it was the case that before Charlotte got here, she'd already taught herself how to fly. And before she could drive a car, she could fly a plane. So the heavens were in her sights from early on. And by the time she got here to Merton, she was clearly far-sighted in terms of her astronomical goals for herself, but busy in lots of other ways as well. As well as very successfully pursuing her passion in physics when she was an undergraduate here, she immersed herself in all sorts of other areas of college life. She was JCR vice president, despite the advice of her tutors. Captain of the Women's Boat Club. She helped out with particle physics schools events. She made a website on string theory. And, demonstrating impeccable taste, was JCR food rep as well, I think. Now, these were just some of the many activities that she managed to combine with being a first-class student in physics at Merton, which, as some of you in the audience will know, is a non-trivial feat in itself. But while she was here, she was also clearly looking for what would come next. And even in undergraduate days, Charlotte was looking for where the next thing would be, applying for summer projects here, there, and everywhere, in order to work out where her career would go. And, well, you ask yourself, armed with all the experience, the knowledge, the expertise of a Merton successful undergraduate physicist, where did she go? She went to the beach. Well, that is to say, she went to the University of California, Santa Barbara to do a master's in physics and astrophysics. A couple of years later, she moved along the coast to do a PhD in UCLA. And by this stage, her star was shining so brightly that NASA picked her up. So she was picked up by NASA as a NASA Hubble Fellow, and then a Center for Astronomy Fellow at the Harvard Smithsonian Center. Actually, I'm not sure if those were concurrent or consecutive. You could probably set me straight on that one. But both very impressive fellowships. And for the last couple of years, she was poached back to Europe and has been an associate professor at the Niels Bohr Institute at the University of Copenhagen. She has a list of prizes that are too long to recount, but they include these fellowships I've mentioned before and the L'Oreal UNESCO Women in Science Prize, which is an impressive one too. Okay, but what is driving Charlotte to the stars? What is she trying to do? It is the quest for the cosmic dawn, that moment when the stars first ignited. And Charlotte's research pivots around that epochal era. It's very important in the history of the universe, and we will be delighted to hear about it today. So please welcome Charlotte, our 30th Ockham lecture.
Okay, thank you very much, Alan. That was very nice. And thank you very much for inviting me. It's really, really lovely to be here. I would say it's quite weird to be on this side of this lecture theatre, but it is really lovely. And so, yeah, this evening I want to talk to you about how we're looking further and further back in time to try and understand what happened in the very earliest stages of our universe. And how this amazing new telescope that was launched into space just over 2 years ago is enabling us to do this for the very first time. And so before I get to all of the pretty pictures that I want to show you, I promise you they're coming, I want to kind of step back in the history a little bit and explain why we're so interested in this period of cosmic dawn and what we've known before JWST about this period and what we're now learning with the telescope. And so I think for, thousands of years, humans have looked up into the night sky and wondered, how big is the universe? How did we get here? What is our place in the universe? And particularly with the advancements in technology in building the first telescopes and the first large telescopes in the last 100 years, we've really been able to, for the first time, actually understand what our place in the universe is. And so there was a big debate in the previous few hundred years of what was the size of our universe. And so as people started building large telescopes, you could see things that were not stars. And so this is an amazing hand-drawn sketch of one of these things that was not a star, drawn in the 19th century by someone looking down a telescope and seeing this kind of fuzzy, swirly thing, which were called spiral nebulae. And there was a big debate about whether these spiral nebulae were actually inside of our Milky Way galaxy or something separate entirely. And it's only been in the last 100 years that we've actually been able to answer that question. And so that advancement came in 1912 when Henrietta Leavitt, who was an astronomer at the Harvard Observatory, discovered that there's a certain type of star, a Cepheid variable star, that pulses. And as it pulses with a very regular period that's directly related to its luminosity. And so if you can measure the period of this star, you should know what its luminosity is. And so if you look at a star that's very faint but pulsing with the same period as another star, that's telling you that that star is much further away. And it gives you a way to actually measure distances. And just over 100 years ago, in 1923, Edwin Hubble discovered a Cepheid variable star, one of these variable stars, in the Andromeda galaxy. And so for the first time, we were able to measure the distance to one of these spiral nebulae and prove that this was much, much more distant than the stars in the Milky Way. And so this really rapidly expanded the size of the universe. So we knew that these galaxies were outside of the Milky Way. The universe is huge. The next kind of step on this distance ladder came not very much later. In 1926, Hubble, looking at the spectra of distant galaxies, the light from these galaxies, realized that the galaxies that were further away from us were also, their light was shifted towards redder wavelengths, so red shifted. And this was evidence that the universe was expanding. And so as the universe expands, the light from those distant galaxies is shifted to redder wavelengths. By this factor 1 plus Z. I have to remember to say Z and not Z now that I'm back in the UK. And so this means that there's a relationship between redshift and distance. And so we can also use this as a way to measure distance out in the universe. And then the thing that at least I think is still one of the coolest things about astronomy is that as we look into space, we are looking back in time. So really, we're time travelers. If I was to explain my job to a kid, I could tell them that I'm a time traveler. And that's because of the finite speed of light. And so if we think about light, things that emit light around us, so the sun, the kind of closest light source to us, does anyone know how long it takes light to travel from the sun to our eyes? 8 minutes, yes. So if you look at the sun, don't actually look at the sun, but if you look at the sun, you are seeing that light that was emitted from it 8 minutes ago. You are looking back in time 8 minutes. And so as we go further and further out, we can see further and further distances, we're looking further back in time. So stars in the Milky Way galaxy, the light emitted from those stars takes 4,000 to 30,000 years to travel across the Milky Way galaxy to reach our eyes. So we're looking back in time thousands of years as we look across the night sky. As we move out to further galaxies that are still quite close to us, so this is the Whirlpool galaxy. It's actually the same galaxy that was that nice drawing of at the beginning. So light was emitted from this galaxy about 30 million years ago. And so you're looking back in time 30 million years. And then the last galaxy that I'm showing you here, this very fuzzy red blob, was the most distant galaxy detected with the Hubble Space Telescope. And the light that was emitted by that galaxy left this galaxy 13.3 billion years ago. And so as we look at these more and more distant galaxies, we're able to look back in time billions of years. And so we're basically trying to piece together this history of our universe by looking at these snapshots going further and further back in time. And so you might ask, how far back can we look? And so we do have kind of the first photo of our universe, which is an image called the cosmic microwave background. So this was light that was emitted about 380,000 years after the Big Bang. It's the first light that we can see in the universe. So before this point, before this light was emitted, the universe was a hot, dense plasma, and so hot and dense that photons basically couldn't travel very far without being scattered by electrons. And it's only when the universe expands enough and cools down enough that atoms can form that the photons can actually stream freely through the universe and eventually reach us. And so what the cosmic microwave background tells us is that what you're seeing basically are these very tiny fluctuations in density or temperature in the early universe. Very, very tiny fluctuations. Really, if you were to look at this map, it actually looks something like this, and you just have to turn up the contrast about 100,000 times to see those tiny fluctuations. But what we can tell from those fluctuations is that most of the matter in the universe is in the form of dark matter, a matter that we can't see. It doesn't interact with light, only via gravity. And then a smaller fraction are baryonic matter atoms that we know and understand. And of those atoms, the majority are hydrogen atoms, so about 70% hydrogen atoms. And so after the CMB, the universe is filled with hydrogen atoms and dark matter and not much else. And a big question is really, how did those tiny little variations lead to all of the amazing structure and complexity that we see around us? So stars, planets, galaxies, the fact that we can sit in this room and talk about this. And at least for me, answering that question is trying to go back to the very beginning and understand how the very first stars and galaxies formed. And this has really been a missing chapter in our history of the universe. So here I'm showing you a kind of a timeline of the universe that's not really to scale. And with the Big Bang here on the left and today on the right. And there's a lot of big numbers in this talk, so I just kind of want to condense this to a timescale that we might be more familiar with. And so let's imagine that the universe is like a 30-year-old. And so for reference, the Earth formed about 4.5 billion years ago. So that would be kind of when you're at university. The CMB on this scale is kind of like the baby photo. So that's about 7 hours on this scale after the Big Bang. And so this period that we call cosmic dawn is kind of the toddler stage of the universe, when we think the very first stars and galaxies form. But up until now, we have had no observational data of this period. So the Hubble Space Telescope has enabled us to observe galaxies in the kind of, I don't know what you would call it, post-toddler age, preschool or something, universe. So redshifts out to about 8. But the James Webb Space Telescope was designed specifically to observe this period, to observe galaxies during this period. And so this has kind of opened the floodgates to seeing what's going on in this early universe. And in the next decade, there's a number of other, particularly radio experiments, actually one that Oxford's quite heavily involved in, the Square Kilometre Array, which will observe gas actually during this period. And so I should say, this has been a complete missing picture in our history of the universe. It's really just been the realm of theory. We have not been able to observe this directly, but we've had some ideas of what we think might be going on, which we can now test. And so what we think is going on is that in about the first 100 million years, those tiny little fluctuations that we saw in the CMB gradually under gravity start to pull together, and you should hopefully see in this simulation that those regions become denser and denser and denser, and then they'll be able to pull the hydrogen and helium gas closer together and gradually get dense enough to form stars. And so in this simulation, you're seeing this process as the gas and dark matter are pulling together, getting denser and denser, and you see all of this structure starting to form. And so these kind of bright nodes are where the galaxies are forming in these most dense regions. And it's not just that these galaxies here are forming in the universe, but they're also fundamentally changing the state of the universe around them, and they drive, we would say, is really the final phase transition in the universe, which is a process that we call reionization. And this is because the photons emitted by the very first galaxies are energetic enough to ionize the hydrogen gas that formed after when the CMB was released. I said that was because atoms formed. But energetic photons from these first galaxies can then heat and ionize that hydrogen gas. Because today we know that really we're back in a plasma again. Most of the universe is a very low density plasma, ionized hydrogen and helium. And so again, here in this simulation, what we think is happening is that these kind of central regions where there are lots of galaxies producing lots of photons from their stars, they're starting to ionize the gas around them. And so we think this process happens in a kind of very bubbly way. So you're building these bubbles of ionized gas around the galaxies until gradually the entire universe is filled with ionized gas. And this then sets the stage basically for all subsequent galaxy formation, is forming in this kind of bath of hot ionized gas. Yeah, sorry.
Are you including dark matter in the simulation?
Yes, so all of this, you have to include dark matter to do any of these things.
How do you do
So maybe we can talk about this afterwards, but we know from the CMB that basically tells us the abundance of dark matter, and it just behaves under gravity. So it's probably the easiest part to model, I would say. Okay, so the questions that I want to address in this talk are what we're learning about when and how the first galaxies formed, when and how was this intergalactic gas heated and ionized, and also I want to briefly touch on when and how were the first metals produced. And so by metals, I mean anything that's not hydrogen and helium. That's what astronomers would call metals. And that's because at the beginning, the only things that were produced in the very early universe, in the Big Bang, were hydrogen and helium. To make any other heavier element requires stars. So in the fusion inside stars and the explosions of stars. And I'm mostly going to touch on these first two topics. And so how do we do this? I'm going to say that there's really two ways that we can do this. So the first is to directly observe the galaxies themselves, measure the properties of their stars and the metals contained within the galaxies. But the second way is also to actually observe the gas itself, or infer properties of this gas in the universe as it's being heated and ionized. And that, in particular, is important, I think, because we only ever really observe the tip of the iceberg when we look at galaxies, because we can only detect the brightest galaxies in the universe. Even with the James Webb Space Telescope, it has a sensitivity flaw. And we think there are many, many more very faint galaxies that we could never possibly detect. But if we can understand what's happening in the gas in the universe, that tells us about the collective input of all of those galaxies. Okay, so I'm going to start off by telling you a little bit about what we know about the galaxies themselves, starting pre-JWST, and then I promise there will be JWST in about 5 minutes. So what do we look at when we look at galaxies? And so most of the time we are concerned with the spectrum of a galaxy. And so this is what I'm showing you here. This is basically the luminosity of a galaxy as a function of wavelength. And the spectra are dominated by the stars in these galaxies. And so here I'm showing you a spectrum of a very young galaxy, which is dominated by its youngest, brightest stars, which are very massive stars. So these massive short-lived stars, they're 10 or more times more massive than the sun. And they're so massive, means they're very hot, and the stars are basically like black bodies. They emit most of their light in the ultraviolet. And so you can see that here, that most of the light is coming in the rest frame ultraviolet. But not only that, because they're so hot and they have these very hard spectra, they produce photons that are energetic enough to ionize a lot of gas. And so all of these spikes that you see here, well, most of the spikes that you see here, come from photons that have been, so for gas that's been ionized by the massive stars and then is recombining. And so a lot of the transitions you're seeing here, most of them are from hydrogen. Most things I haven't labeled because it's just all hydrogen. There's lots of oxygen, carbon, magnesium, et cetera. And so that's actually what we see if you look in this image. This is the Orion Nebula, which is the fuzzy part at the end of Orion's belt. And in Orion in particular, most of this kind of glow here is coming from the Balmer line, hydrogen alpha, which is about 6,500 angstroms. And so this is a very young galaxy. We can also see the galaxy population, the stellar population change. So if once these massive stars die, the spectrum is dominated more by solar mass, or smaller solar mass stars, which emit most of their light in the optical wavelength. And so by looking at these spectra, we can both tell about the stellar populations inside these galaxies, their ages, but also the chemical enrichment inside of these galaxies. Usually we don't spend a lot of time looking at these detailed spectra because they require a lot of signal to noise to get something as nice as that. And so an efficient way to do it is basically using broadband spectroscopy. So we take images of galaxies in broadband wavelength filters. And so this is what you're seeing here, an example from the Hubble Space Telescope, where we've used 4 different filters in different wavelength bands to observe a galaxy that probably looks something like this, where it was the same spectrum that I showed you before, but now it's redshifted into the infrared or the near infrared because this galaxy is much, much further away. And so when we look in the images, we basically see these blobs in the redder filters and nothing in the bluer filters because the UV light of that galaxy was shifted all the way into the near infrared. And so this is basically how we can detect these galaxies, is for looking at things that show up in the red filters and then drop out of the blue filters. And that basically tells us the redshift of that galaxy because it has exactly the same shape as the spectrum that I just showed you before. And so cutting 30 years of the Hubble Space Telescope very quickly, I would say one of the most interesting results from Hubble was that we're now basically in a declining universe. If we look at the amount of star formation happening in the universe as a function of time, we're really in a decline now. And so most of the star formation in the universe happened about 10 billion years ago. So between a redshift of about 1 to 3. And we're now in this period of decline. And at some point, at very high redshift, we're going to this period of cosmic dawn when the first galaxies formed. And so how can we understand this evolution? And I think there are many ways that we can think about this. I asked the question a number of years ago, like, what's really the simplest way that you can try and do this? This is kind of in the spirit of Ockham, I guess. Like, what's the simplest model that you could come up with to explain this picture where stars are forming and then dropping off? And so I think this picture is really of how galaxies are forming. I would have in your head of the galaxies are forming inside these giant dark matter halos. So when I mean halo, I just mean a kind of a big blob of dark matter, which is kind of like the scaffolding for where the galaxy is forming. And that provides a strong gravitational potential that pulls in gas to fuel star formation. And so in this kind of illustration that you're seeing here, you basically have gas being, my laser pointer doesn't work, but you have gas being pulled in into this gravitational potential. It can heat up basically as it's losing potential energy, so it has to be able to cool down again, which it can do by radiating. And then as the stars are forming, you can then also have particularly supernovae then exploding and pushing gas out, heating it up. So there's this kind of recycling process of gas coming in, then gas being ejected, and this kind of constant stream of star formation cycling. And so, we basically said, the simplest model that we could think of was that the rate at which a galaxy forms stars is proportional to the rate at which gas is accreted, multiplied by some sort of efficiency of turning that gas into stars. And this efficiency looks something like this, as a function of the dark matter halo mass, basically the potential well. And so what we find, and this is seen by many people, that there's a kind of a peak of this star formation efficiency. Turns out the halo mass is about 10 to the 12 solar masses. It's actually very similar, we think, to the mass of the Milky Way. And it declines at lower and higher masses. And in the highest mass halos, we think this is due to large accreting supermassive black holes that can heat and eject the gas. And in low mass galaxies, we think basically that the gravitational potentials are so weak in those galaxies that it doesn't take that many supernovae to explode and push out all of the gas, that it's very, very hard again to form new stars. And this very simple model can actually explain this evolution in the rate of star formation in the universe really kind of remarkably well. Like, it had basically 2 ingredients. And so here I'm showing this model compared to the observations. And the explanation here is basically that as you go from the highest redshifts in the early universe up to the peak, it's because these galaxies can accrete lots of gas to form stars, and because the halos, the dark matter halos, are gradually merging together, getting bigger, and getting into this regime where they're more stable and basically more efficient at building stars. And as we go into the later universe, the accretion rates are slowing because the universe is expanding, and halos are getting more massive and then again less efficient. Okay, so that's what's going on in the galaxies that we've been observing, but what about the gas around them? And so this is something that we can study by basically shining really bright lights through the gas. If I want to understand how this bubbly ionization of hydrogen is happening, I can shine a really bright light through the bubbles, so basically look at the galaxies themselves, but observe the imprint of the neutral gas on the spectra of those galaxies. And so we do this looking at the Lyman-Alpha emission line. And so this is where I'm glad that I did, I don't know, I feel like I don't know if Simon remembers this, but I feel like I wasn't very good at atomic physics, but I understood hydrogen. So I mostly just work with hydrogen. So Lyman-Alpha is the n=1 to n=2 transition in neutral hydrogens, the transition to the ground state. And it has a wavelength of 16 angstroms. And it's really the strongest, most ubiquitous emission line in young star-forming galaxies. So here I'm showing you a spectrum of a young star-forming galaxy, and you see this booming line, which is this Lyman-Alpha line. And it's produced, as I was saying before, predominantly these emission lines come from recombination. So these massive stars in these galaxies ionize hydrogen around them, and as the hydrogen recombines, something like 2/3 of all the recombination events lead to the emission of Lyman-Alpha photons as they're cascading to the ground state. And the cool thing about Lyman-Alpha is that it has a very high cross-section for being absorbed by neutral hydrogen. And so this makes it kind of a smoking gun of this reionization process. So once the gas in the universe gets over about 10% neutral, we should expect most of the Lyman-Alpha photons and photons bluer than Lyman-Alpha to be absorbed by the neutral hydrogen in the universe. And so if we were to observe this galaxy that had this nice strong Lyman-Alpha emission line in the high redshift universe, we expect to see something like this, that basically all of those photons, Lyman-Alpha and bluer, are absorbed by neutral hydrogen in the intergalactic medium. And so this is something that we've been trying to do for the last sort of decade or so, is to basically make this measurement. So going out and looking at galaxies at higher and higher redshifts and measure the amount of Lyman-Alpha emission that we see from those galaxies. And what we've been finding is that when you get to redshifts above about 6, so about 1 billion years after the Big Bang, the amount of Lyman-Alpha that we see in these galaxies rapidly drops. And so this is some of our strongest evidence that the universe at this point is becoming increasingly neutral, and that cosmic dawn is somewhere not too far from here. But what is happening in these earlier stages? And this has been really, really difficult to do. So this is kind of like the state of the art of what these measurements have looked like prior to JWST. So this is a spectrum of a redshift 7.7 galaxy, where I've nicely highlighted the Lyman-Alpha emission line for you in purple. I think if I hadn't put that there, you might not have known where it was. This is like tricky stuff. There's a lot of, it's really hard to detect light from very distant galaxies. You can see, so the solid black lines here are the signal, and the gray shaded regions are the noise. These are very, very faint. You can also see there's these big spikes in the noise at certain wavelengths, and those correspond to emission in the Earth's atmosphere. Oops. So the particularly OH molecules in the upper atmosphere emit lines basically in all of these redshift wavelengths that we're interested in the infrared. So this is a beautiful spectrum of the sky, which is most of what we observe when we're actually trying to look for these galaxies. So it's really, really difficult to do. And that kind of is one of the main motivations for the James Webb Space Telescope, is to get out of the Earth's atmosphere. And so James Webb, now I'll show you the pretty pictures, was really designed to observe this era of cosmic dawn, pushing into the infrared outside of the Earth's atmosphere, so we don't have to worry about the Earth's the contamination from the Earth's atmosphere. So this is the telescope in the clean room at NASA Goddard. So this is just the kind of science part of the telescope. So this is the mirror. And you can see there's the big primary mirror and there's a secondary mirror that's folded up on top of it. And you can see it's very, very gold. And that's not just because we like things to be gold and shiny. I mean, we do like it to be gold and shiny because the gold is particularly good at reflecting infrared light, which is what we want if we want to look further back in time. And so the telescope was, I mean, it's a long time in coming. So this, I think it's kind of one of these projects in physics that gives you an idea of like the time commitment and scale of these projects. This has been over 30 years in the making. So it was first conceived in 1989 and finally launched on Christmas Day in 2021. And certainly, I know many people who have worked on this for nearly 30 years. I started my PhD thinking that I would get data from the telescope during my PhD. And it took, 11 years, I guess, or 9 years since we got the data. So yeah, it's been a long time coming, but it's been really, really exciting to be kind of in this moment and watching the launch on Christmas Day. I mean, unfortunately, I didn't actually get to go to French Guiana. I know a few people who did to see the launch, which must have been pretty cool. And this is the last view that we got of the telescope, kind of sailing off into its position. I'll talk more about that in a minute, where it is. But one thing you can see is it actually looks quite compact here. So the telescope is so big, it's about the size of a tennis court, that it couldn't actually fit inside of the rocket. It had to be folded up, kind of like origami, and then gradually unfurl itself in space, which was, I think, probably a terrifying thing to have to work on. I think there was something like over 400 different ways that process could fail, but not a single thing failed, which was actually really remarkable. If anyone, I don't know how many people have seen this, there's quite a fun documentary on Netflix about like all the ways that it could fail, which is nice to watch. But nothing failed, and it's actually now performing in every way better than we had expected, which is amazing. So after about, launched in December 2021, and then there was about a 6-month period of commissioning where they were basically turning everything on, testing that everything worked, calibrating stuff. And then we finally got the data in July, or the first science data in July 2022. And so what I'm going to show you now, probably many of you have seen, is the very first science image that we got from JWST. And I think just to give you kind of a bit of sense of scale of this image, the size of the area on the sky that you're seeing here is about the size of a grain of sand held at arm's length. And so pretty tiny. And you just see this image is completely filled with galaxies. Thousands and thousands of galaxies here. I think if it was a bit darker in here, actually, you could see more things. You can see a few stars. So these things with the spikes are the stars, the diffraction spikes. It's kind of cute because you can see that this was a JWST image because they have 6 spikes, and that's because the mirror is a hexagon. So if you want to be able to tell what's a JWST image, look for 6 spikes. So this image was revealed to the world by Joe Biden. I guess he decided this was something that he felt was good to share. So I hope he liked it. But yeah, it's at least for astronomers, this was a kind of amazing thing to see. We didn't actually get real data for the first couple of days. They just sent us the pictures. So everyone was kind of like zooming in on the image, trying to figure out what was going on. But yeah, it was a pretty fun time. And okay, so why is JWST so exciting? So the first thing is that it's really extending our wavelength coverage into the infrared. So Hubble could observe to just over 1 micron, and JWST can observe from just under 1 micron to about 25 microns. So it's not really, I would say, the successor to Hubble, but kind of like the cousin. And this wider wavelength coverage, or redder wavelength coverage, means that we can detect galaxies at higher redshifts, look further back in time, And it also gives us a broader coverage of their spectra. And so to work effectively in the infrared, the telescope has to be cold to reduce the infrared background. And so for this reason, it's positioned pretty far away to stay as far away from the sun as possible. So it's about 1 million miles away from Earth, whereas Hubble is actually in orbit around the Earth. And it's in this position called L2, which is a Lagrange point of the Earth-Sun orbit. So it's a stable point, and then it's basically in orbit around the sun right behind the Earth the whole time. And it always needs to be pointing away from the sun to keep it as cool as possible. So it's actually sitting on top of this sun shield that's many layers of a kind of foil that act as an insulator and keep it very, very cold. So on the sun side of the sun shield, it's up to about 90 degrees Celsius, whereas on the other side, away from the sun, on the other side of the sun shield, it's about 40 degrees above absolute zero. And I think someone told me that's an SPF of about a factor 1 million, which I thought was a cool fact. So it keeps it nice and cold. It also makes it a little bit difficult for finding the right time to look at the part of the sky that you're interested in, because it always has to be pointing away from the sun. But I think there are people who write very fancy algorithms to think about that. Because it has such a big mirror, it's a much bigger mirror compared to Hubble, it means it's much, much more sensitive. It's able to detect much fainter light than Hubble could in the same amount of time. So here I'm showing you a comparison of the same image that I just showed you. On the right, the one taken by JWST, and on the left, the image taken by Hubble. And you can see that the image taken by JWST is there's much, much more going on. You can see many more of the very faint galaxies that you couldn't have ever detected with Hubble. The larger mirror also means that it has higher spatial resolution. So on the left here, I'm showing you an image taken by the Spitzer Space Telescope, which was operating at a similar wavelength range to James Webb. And you can see these kind of blur. And now with JWST, we can see that these blurs are actually both galaxies, and then you're actually resolving individual stars in this. This is a dwarf galaxy, which is a very diffuse galaxy quite close to us. So all of these little dots are actually stars in another galaxy. The fact that we're observing in the infrared also means that we can see a whole lot of new things that we haven't seen before with amazing resolution. So on the left, I'm showing you an image taken by the Hubble Space Telescope of a nearby spiral galaxy, where most of the light you're seeing, the kind of blue light, is coming from star-forming regions. And the red light is dust that's kind of blocking our view there. In the image on the right, taken by JWST, you can see dust. Most of the light is coming from the actual dust itself, which is emitting in the mid-infrared. And more complex molecules that also emit at these wavelengths. The other thing, it shows up quite so well, but I think is really cool in this image is, I don't know if you can see where my laser pointer is. There's this blob that's right here, this kind of dark patch. So these kind of circles that we're seeing are basically regions that are clear of gas and dust. And people think are probably basically bubbles carved out by supernovae. So as stars explode as supernovae, they push gas away, and you're left with these kind of bubbles that are completely cleared of gas and dust. So there's a lot of really cool things to look at in these images. Okay, but the thing that I've been most excited about is the spectroscopy, and not having to deal with the Earth's atmosphere. Because the telescope is so sensitive, it has this large mirror, it has very sensitive spectrographs. And the fact that it actually has spectrographs itself is amazing. It has these high-resolution spectrographs. Is kind of mind-blowing. So this is a spectrum taken by the Hubble Space Telescope. So Hubble had a very low-resolution near-infrared spectrograph. And this was the most distant galaxy confirmed by Hubble. And so you, again, see this spectral shape where you see this light that's emitted in the near-infrared, or observed in the near-infrared, but would have been emitted in the rest frame UV coming from massive stars in a very, very distant galaxy, a galaxy at a redshift around 11. Very noisy spectrum. This took about 18 hours on Hubble. And obviously, this was one of the first things that people thought, right, let's go observe this with JWST. And there is, what I will show you now is a pretty amazing spectrum, which I think just gives you a sense of like how much better this telescope is. So this is the same galaxy. This is from actually a paper by Andy Bunker, who's in Oxford. I don't know if he's still teaching he was teaching the second year astro course, I think, when I was here. So he got very lucky to be able to observe this, I think. So yeah, it's amazing for many reasons. So the first thing I think that you can see is that it's extremely high signal to noise in a fraction of the time that Hubble had. So this is only in 7 hours. It's also, you can see this very wide wavelength coverage. So Hubble could only see out to about 1.7 microns. With JWST, we can see all the way to over 5 microns. So that means we have a much wider range of this galaxy spectrum. We can get a lot more information about what is happening inside of this galaxy. And you can see then all of these different emission lines that I seem to have deleted my labels to. But you can see all of these different emission lines coming from all of these different elements inside the galaxy. And I think one thing that's actually quite exciting is if this is a galaxy, this is a redshift 10.6. So this is just, 400 million years after the Big Bang. But we can actually see a lot of heavy elements inside this galaxy. So, there's hydrogen emission lines, but there's also emission lines coming from carbon, nitrogen, oxygen, neon. I didn't even know there was neon in these galaxies. So the chemical enrichment of these galaxies must have been very, very rapid. I think a kind of holy grail for us is to basically find, the first galaxy will be one that we can just see hydrogen and helium in, because the very first generations of stars, that's all that they would have had. But we can already see with these galaxies that there's a lot of other heavy elements being produced in them. There's been successive generations of star formation. We are seeing with JWST, it's much, much easier to detect this Lyman-Alpha emission that I was talking about before. So these are a couple of examples. So the top one has a nice, strong Lyman-Alpha emission line. The one at the bottom doesn't have any Lyman-Alpha emission line. And so in terms of this understanding the process of the reionization, with JWST, we seem to be confirming what we'd seen before, that as we go to higher and higher redshifts now, for the first time, we can look at redshifts greater than 8. There's this really rapid decline in the amount of Lyman-Alpha, which is implying that the universe is getting much, much more neutral at these early times. And that's something I've certainly spent a lot of time figuring out, how to go from these Lyman-Alpha measurements to saying something about what's happening during reionization. But so here I'm showing you the fraction of hydrogen in the universe that's neutral as a function of redshift. And we think now with JWST, we're getting up to the point where the universe is nearly 90% or more neutral in hydrogen. And so that means that we're really closing in on this period of cosmic dawn, because once we're in this completely neutral universe, that's really when the first galaxies are just turning on. And so we think basically above redshift of 10 is this period then of cosmic dawn. So what have we seen? So I was part of one of the early release science programs, which was programs that were designed to kind of test JWST's capabilities. So we observed in the first 6 months of the program. We actually observed in the first week of the science program, which was a bit nerve-wracking. And one of the things that I did was design the imaging part of that program, which was also quite nerve-wracking. That was it going to work? But these were the images that we took. And as part of that program, we had predicted that based on what we'd known about how we thought galaxies were forming from what we'd done with Hubble, that we would get there was about 20% chance of detecting one galaxy at a redshift above 9 in this image. There's 2 panels next to each other. And what did we find? We found 2 extremely bright galaxies at redshifts above 10. And this was really, really unexpected, I would say. And this has been kind of like one of the, for me, I think one of the most interesting things coming from the early stages of JWST. We're seeing lots of these kind of fuzzy little blobs that you can't really even see in the image. You have to zoom in a lot. But these are these very, very distant galaxies in the early universe. And in fact, it's not just us, but overall, across the board now, we think we're finding about 10 times more bright galaxies in the very early universe than basically any theoretical model had predicted. So here I'm just showing you the same model that I showed you at the beginning, with the new measurements from JWST in the triangles that are about 10 times higher than this model. And this is just one example model, but most other models find exactly the same thing. And we're really seeing this excess in very bright galaxies at these very early times. So why? This has been kind of a big puzzle, I think, in the last 18 months is why are we seeing all of these very bright galaxies in the early universe when basically every model has told us that this is when we should see things tailing off. And so this is something that I have been thinking about a lot and trying to come up with some various ideas for what might be going on and trying to think, what is the simplest solution to explain these things? So there's a number of different things that I will try and go through and then try and tell you about the things that I think are most interesting. So one scenario is that the galaxies in the early universe are less dusty. And so dust, I was showing you that spiral galaxy that had all these kind of dust lanes in it that's produced by supernovae and stars, absorbs UV photons and re-emits it in the infrared. So if we get to an early time where these galaxies haven't had much time to produce dust, then less of the UV photons are being absorbed. So that's one possibility. A second possibility is that not all of the light is coming from stars. We also know that accreting supermassive black holes will emit light in the ultraviolet. So maybe that's also contributing here. Another scenario is that galaxies are forming not in a kind of smooth way, but in a very, very bursty way. So kind of like these fireworks going off where you can temporarily be much brighter than average. Maybe it's easier to form stars in the early universe. Or maybe the stars themselves are different. If the stars are much hotter and brighter, then this could be producing these brighter galaxies that we're seeing. Maybe we just got lucky. Maybe we have been observing very high density regions of the universe where there are just more galaxies. Or maybe cosmology is wrong. So I said I'm not going to start with that one. I think we figured out that the dust thing is probably not really significant. We know that these galaxies are less dusty. We've seen that already with Hubble. And so this is not really a significant effect at these redshifts. The accreting black holes, with JWST, we are finding actually a lot of evidence for more accreting black holes in the early universe. But it actually seems like most of the light from these black holes is obscured in the ultraviolet, which probably suggests they're surrounded by a lot of dense gas and dust. So they're probably not contributing to the UV light that we're seeing. And I don't think we just got lucky. We've now been observing many fields in the sky and basically confirming the same thing. So I think this is telling us that something is different about the ways that stars are forming in the very early universe. And I think probably it's some combination of all three of these things, and I'm not sure yet which is most important. But we know that, or at least we think that probably, at least from simulations, that the star formation probably is much more bursty in these early galaxies. So this is a simulation of, so an example from a simulation showing the star formation rate in a galaxy as a function of time. And you can see it goes up and down and up and down and up and down. And we think this is probably more common in these galaxies in the very early universe because the halo masses, so the dark matter halos, are much less massive, so the gravitational potentials are much smaller. And so that means that it doesn't, if you've got some stars forming, it doesn't take that much energy to eject all the gas. You've run out of fuel for a while, and then you have to wait, accrete more gas, and then you can form stars again, and then you blow out all the gas again. And so this process kind of keeps going on until the galaxies got big enough, their halos got massive enough that this process kind of stabilizes and you stop blowing everything out. And what this then predicts is that there's kind of we might observe galaxies in kind of two different modes. A kind of an on mode where you're seeing galaxies forming lots of very massive young stars right at that moment. And then an off mode where the galaxies are not forming stars right now. Most of their massive stars have died off, and we would just see the lower mass, longer lived stars. So are we seeing this? And so with JWST, we can actually characterize these galaxy spectra, as I showed you before. And so most of the spectra that we're seeing do seem to be dominated by young massive stars. So here I'm showing you another one of these spectra that has all of these strong emission lines, so suggesting that there's young massive stars. But we are also seeing some evidence that there are galaxies in this kind of off mode. So this is a galaxy at redshift of 7, where it doesn't have these strong emission lines. It has some UV emission, but not that much. And it actually has quite a reasonable amount of emission in the optical, suggesting that it's starting to become more dominated by the lower mass stars, and the most massive stars are dying off. So this is potentially some evidence that this off mode does exist, and we're getting this evidence for this bursty star formation. But I would say that probably most of these galaxies are way too faint to actually detect at the moment. So if we want to find more of these things that are not forming stars, we're going to have to observe for much longer. But I think they are out there. And I think we're also finding evidence that the stars in these galaxies are very massive. So this is maybe too complicated a plot, but for the end of this lecture. But here I'm showing you basically a plot that's telling you about the energy of the spectrum in these galaxies. So on the x-axis, it's the ratio of singly to doubly ionized oxygen emission lines, and the y-axis is the strength of doubly ionized carbon. And so to doubly ionize carbon and to doubly ionize oxygen requires really energetic photons. And so in the top right of this plot is kind of the most energetic photons. And so what you can see is these different colors correspond to galaxies at different redshifts. So the galaxies at redshifts 0 to 3, the kind of more local galaxies, span a pretty wide range in this plot. But the galaxies in the highest redshifts that are now being observed with JWST are really only in the top corner of this plot. So those galaxies are dominated by stars emitting very energetic photons, and probably photons that are of stars that are over 100 solar masses, which seem pretty different from most of the stars and galaxies that we're seeing today. Okay, so I think I'm going to end here. And I've told you that JWST is already confirming that galaxies exist 300 million years after the Big Bang. But we're seeing that their light is dominated by young, massive, hot stars, but they're already chemically enriched. So we know that the metals in these galaxies are being formed very, very quickly. We've learned that the intergalactic hydrogen in the universe was ionized within about the first billion years after the Big Bang. And so that tells us that cosmic dawn must have happened fairly soon before that. And the early results from JWST, I think, have been really exciting in that they're telling us that the way that stars form in the early universe seems to be very different from how it is in the later universe. And in particular, I think we're seeing this shift to a much more kind of stochastic star formation, and that the stars themselves are probably more massive than they are in the later universe, because otherwise we just can't explain the abundance of galaxies that we've been seeing. And so I think this is a pretty exciting time. I think we've kind of had this, open the floodgates to seeing what's out there. And I think in the next few years, there's going to be a lot of progress in trying to understand what's really happening in these galaxies at cosmic dawn. Thank you.
For this, and this is a signal for us to open the floodgates and for the young, massive stars in the audience to burst out with their questions. So, questions?
You said that there's lots of stars with more than 100 solar masses forming in the early universe. Wouldn't there be a problem of a direct collapse to black holes sort of stopping stars forming above certain masses? I mean, I'm not exactly sure what the number is, but is that sort of a problem with that theory, or?
Yeah, I guess I'm also not exactly sure what the number would be too, but yeah, I mean, we also, I think, don't really understand massive stars in general, so there are lots of things that we don't understand. Probably if you get above a certain mass, you can directly collapse to a black hole, but we actually have, we have evidence in the local universe that there are some stars that are 100 to 300 solar masses, so they can exist. Yeah.
On those images where you were describing how you were quite surprised by like the density of galaxies with really, really high redshifts above like 10 to 12, what was the field of view, roughly?
The field of view, yeah, it's the same. So basically they're all kind of the same, right? The camera is the same size, so everything is a grain of sand at arm's length.
Okay.
But if you want it in square arc minutes, I can also tell you that. It's just 10 square arc minutes.
So how many of those
Yeah.
kind of tiny grains of sand have you sampled roughly?
Yeah, so that's a really good question. So when that image was first taken, that was the only one. So I think it would have been a very good thing, a reasonable thing to say, have we just got lucky? But at this point, I think we're now up to about 100, or 10, what am I thinking? What number am I thinking? Not 100 times that. 300 times, so about 30 times that. And I also have an observing program running at the moment, which will get 80 times that, I think. Because that was the question I asked, was like, have we just got lucky? So we're doing this kind of fun thing where we're just like randomly sampling places all over the sky. So I think at this point, the more and more fields we observe, it does seem like there are more galaxies out there everywhere. But it's a good question, yeah.
Thank you.
Thank you very much for your talk. Outsider question. Are there any mechanisms predicted for the shift to more bursty star formation and of the formation itself?
Yeah, I mean, I think the main thing is this argument about the gravitational potential. So, you know, once the gravitational potential increases enough that you're not going to, there's a kind of a binding energy, basically, that the supernovae, if a supernova goes off, it's not going to eject too much of the gas. And so the argument is that basically, I think once you get above a certain redshift, these dark matter halos are merging together, and then they become more massive, and at that point you kind of stabilize yourself against this very bursty star formation.
So it's purely classical effect.
Yeah, and it's
no.
Yeah.
So perhaps you said this and I might have missed it, but you said that these earliest galaxies observed have non-negligible presence of what you would call metals. Is there any non-negligible presence of elements heavier than iron?
Not that I've seen convincingly.
Okay.
Yeah.
Sorry, am I correct in thinking that elements heavier than iron are only formed in supernovae?
Yeah.
Because I was just wondering if they're provably first-generation stars.
Yeah.
First of all, you almost killed me when you called as a chemist, when you called everything that is not hydrogen or helium a metal. But besides that, once again, a really chemistry question, I guess. I'm aware that when we look at this kind of emissions, we tend to see mostly even number nuclei being present of atoms with an even number of protons, basically, being represented because of the kind of system in which the kind of reaction, let's say, through which they form. But I've seen a lot of nitrogen lines, which is the only odd one I can, besides hydrogen, but that doesn't count. It's just a proton at that point. But why is that? Like, is nitrogen more easily formed compared, for example, to fluorine or lithium?
That's a really good question that I think I would have to remember more of my stellar evolution physics for. But I mean, there is a process by which nitrogen is formed quite easily in stars that I cannot remember all of the physics for.
Also, like, when you talk of dust,
yes.
And I'm aware that in later galaxies, that dust is actually the base of many forming of, let's say, molecules in space, but that's much later in time. What is that mostly composed of? Is it carbon?
Yeah, that's a good question. I think mostly sort of carbon and silicon molecules, yeah.
Thanks for your talk. It was really nice. Because I'm interested in the theory behind the simulations, what's actually going on with these simulations, basically? Like, how are you able to simulate these things and take away some physical meaning from them? Like, what are the approximations that are made?
Yeah, that's a really good question. So I would disclaim I did not run any of these simulations. I just like the movies. But usually, basically, I mean, you can start, so I'm not an expert on doing these things. I like to do very simple toy models. But, you know, you can take the initial conditions which we get from the CMB, and which is basically saying that the distribution, there's a kind of Gaussian distribution of these initial density fluctuations, and then just kind of turn gravity on, and they will eventually, gravity and the expansion of the universe, and they grow in a particular way.
Like Newton's law of gravity, basically. When you're saying turning it on. When you're saying turning gravity on, do you mean just 1 over the distance squared or 1 over r?
I think in most, I think in most of these, yes, it's just Newtonian gravity. Yeah.
Yeah, it's just the dark matter is
Yeah.
just the infinitely compressible self-gravitating stuff.
Yeah.
When you say dust, I know that you're talking on like cosmological timescales, which are massive. So how big are your dust? How do you know roughly how big your dust particles are?
Do I know how big they are?
We know.
Do we know? Then I don't think we do know. I think that's a really good question. I was actually at a conference a couple of months ago where there was like this huge debate about how big are the dust particles, because someone was like, they can be shattered by something makes them shatter and something else makes them coalesce, and we don't know which one is going on. But millimeters, micrometers, that kind of scale, yeah.
I have a question as a member of the general public in the room. You said that the JWST was proposed in 1989, but I don't think I'd heard of it until shortly before it was launched. And obviously it's blown Hubble out of the water. Have there been any other space telescopes proposed in the last 30 years that are going to come online in sort of 10, 15, 20 years' time?
Yeah, I mean, there are a few. I'm trying to think of what would be the next thing that you might start getting excited about. I've actually lost track a little bit. There's been kind of like ongoing debates about what the next thing should be. And I'm not 100% sure what's going on with that. I think there's been like several different missions that have been proposed as the next big thing that are being kind of discussed. I mean, I think the main thing is really a real successor for Hubble, because Hubble is slowly degrading, and it's the only thing that can observe in the UV and the optical in space. So whatever that is, there is something that I can't remember the name of that will be the next Hubble. I don't know if anyone else knows the name of it.
There's Athena in X-ray. There's Athena.
Yeah, Athena links. So, but that's X-rays. So, as I say, there's several things posed to do different wavelengths, and it's not clear. They will all happen eventually, but hopefully.
Astronomical tribes separate by wavelength.
Yeah.
Right? So they compete whose wavelength is better.
Yes.
Right.
I have a question. I've got a microphone, so I can ask it just without doing it. Are we really ignorant of everything that came between the CMB and cosmic dawn? Is there anything that we know about that observationally?
Observationally,
at all?
Not really. I mean, we have some. The CMB tells you some things. So basically the CMB can be scattered by. Well, I mean, it tells you a bit more about the reionization process. The CMB photons can be scattered by the free electrons that are created during this reionization process. So if some ionization happens quite early, that would scatter some of the CMB photons at particular scales. But other than that, basically no. But this is where, I mean, so both JWST and then in the future, these radio telescopes that will observe the neutral hydrogen gas itself, that can tell us about just the gas in the early universe.
I feel mean for asking, because you just told us you did spectroscopy from 13 billion years ago in detail, and I thought, okay, but what else can you do?
So what I've known so far is basically when the JWST approaches to a higher wavelength region, say like 20, 25, 27, the signal it gets is very noisy. Is there a way for us to denoise it? And also what impact would it make to our observations?
That's a great question. If you can tell me how to denoise things. Yeah, I think the longest wavelengths are limited by the very far infrared spectrograph just isn't as sensitive as the near infrared spectrograph. I think it's just probably less efficient at receiving the very infrared photons. I don't know if there's really a way to really denoise it if you're reaching kind of the instrumental sensitivity.
So reaching the limit of the observation.
Yeah. But it's still much, much better than anything that existed before. I think can't complain too much.
Perhaps I'm just sort of lacking in sort of background pop science knowledge, but on your grain of sand images, there seemed like sort of like the galaxies and things looked like they were sort of slightly curving around something.
Oh yeah.
In the middle. Is that what causes that?
Yeah, that's gravitational lensing, which I completely glossed over, but this is really cool. So the kind of the white fuzzier galaxies in the center of this image, and then there's quite a lot of them around, are a galaxy cluster, so kind of like a city of galaxies that are all living close together. Basically it's a huge gravitational potential. And so light from distant galaxies, as it travels through this gravitational potential, is warped. Light has to travel in geodesics, and that's warped by this gravitational potential. And so what you're seeing, these kind of red arcs in the background, are actually distant galaxies that have been warped, this gravitational lensing effect. And so probably, I have to figure out a good way to see this, probably they can actually be multiple images, so it's the same galaxy that you're seeing in multiple places. So some of them, you can see these kind of streaks, and they kind of form these arcs around the galaxy. You can see another one, actually that kind of crazy looking one right at the top, the red one, I think is being gravitationally lensed just by that bright white galaxy that's in the foreground. So it's also arcing around it. So this is pretty cool. This is also kind of a cool technique because the gravitational lensing also magnifies the galaxies. So we can use it to look at even more distant galaxies and get them in kind of high resolution as well.
Was that Hadley turning around to say, that was on your last problem set?
Yeah, I was just curious because I was thinking of space missions, and I thought about LISA and the other gravitational wave thing. Mm-hmm. Is there any role of gravitational wave astronomy in trying to figure out early galaxy formation?
Yeah, I mean, I think certainly in terms of understanding the formation of black holes in these galaxies, there's been a lot of debate in the last few years about, I mean, even before JWST, people finding supermassive black holes in galaxies, kind of the edge of Hubble, so redshift 7, and trying to understand how those galaxies, how those black holes got so massive so early. And so we should expect some kind of gravitational wave signal coming from various causes of how these supermassive black holes formed, if they're coming from lots of mergers in the early universe, or if, depending on basically the size of the seeds of the black holes. So there is, definitely potential for LISA to answer those questions.
Hi, so for those first two galaxies you found in 2 weeks, how manual is the process, or is it AI, algorithmic, or just zooming in on a map?
It's a sort of a mixture. So, I mean, it's mostly automated, right? Because there's these images, there's like thousands of galaxies here, so you do whatever. So we have some kind of like image segmentation algorithm. So you look at this and you get rid of all the black and say, okay, this is a galaxy, this is a galaxy, this is a galaxy. And then for each galaxy, we have, images at all those different wavelengths. And so you can then make a kind of low resolution spectrum of every galaxy, try to fit that with some template that would then tell you what the redshift should be. And so then you could just kind of have an algorithm that tells you, okay, this is my long list of galaxies that I found in this image. This is what the redshift probability of this redshift is. And then you want to go through them and actually look at the images and check that it is what you think it is, because there's like random, I mean, especially the very early stages, it was kind of crazy. Like there were all these calibration issues. Certain parts of the detector had different flux calibration than the other part, and there were like these wisps and snowballs and I don't know what weird detector things that people were trying to figure out. So you do have to like go and then look at all the images afterwards and see if you really believe the thing that your algorithm spit out.
How do you tell the difference between a redshifted galaxy and, if such a thing exists, a galaxy populated largely by quite cold, small red stars?
That is a great question. That prior to JWST has been really hard to answer because you often can't, because they basically can look the same. So with Hubble, that has been a really big problem. With JWST, at least up to redshift, I don't know, 14, you can see enough of the spectrum that you can tell the difference between the two. Or you can actually measure the emission lines, and that definitively will tell you this is the redshift, which is why having the spectroscopy is so important. But above redshift 10, things start to get more challenging, and at redshift 14, it is still challenging. And actually, there was a very prominent example of a galaxy found kind of the same time period, and within a few weeks of the launch, a galaxy claimed to be at redshift 16. And then it was observed again with the spectrograph. So that just with initially they're just all observed with the imaging, the kind of low resolution spectroscopy, and then it was observed with the real the high resolution spectrograph, and it was found to be at redshift 5, so much closer. And it was just the same effect that this galaxy that was closer to us and had the kind of the lower mass stars looked like the higher redshift one. So it's a really important thing that we have to try and figure out. But most of the time we can do it with the spectroscopy. Yeah.
Right. Maybe since I have the microphone, I could ask a question as well. You mentioned that the sort of outside possibility for the explanation for the brighter galaxies at high redshifts was that cosmology was wrong. So if you like, we could turn off the camera and Chatham House rules. You could tell us. You could tell us about. So what's the story with that? What in what way does it have to be wrong in order for?
Yeah, I mean, I think there are some arguments. I mean, I think this particularly had come from people trying to actually measure the stellar masses of the galaxies, which I think is actually a really difficult thing to do at these redshifts because most of the light is so dominated by the massive stars that it's difficult to measure the stellar masses. You can't see all of the stars. But in those, when people then compared the stellar mass to the expected halo mass, then the stellar mass was often larger than the halo mass that you would expect in kind of a standard cosmology. And so the argument there is that there are more massive halos at high redshift than we had expected, which could, mean that there's some difference in the power spectrum. But I think it's hard to do that and still be consistent with like results from Hubble and the CMB and stuff. So I think it's the last thing to look at, I would say.
Why were the mirrors designed diagonally? Not diagonally, hexagonally.
Hexagonally. I think it's just because if you want to build a really big mirror, that's the easiest way to do it without it like collapsing, probably. Because they're kind of segments that you can just put together. You can't really build like a circular thing that big, I think.
Right.
Yeah.
It's maybe not directly related to exactly what you did, but you had there at the start this image or like a video of galaxies and everything kind of forming, and it made this kind of like a webby pattern where it was kind of like stringy and it had vertices and stuff. Mm-hmm. Do you know like what causes this kind of like string and like vertex like structure? Like is that like a consequence of, I don't know, the plasma bubbles, or what is behind that?
Yeah, that's a great question. So it's called the cosmic web, I guess because it looks like a web. And it's really just a consequence of the way that the structures are forming under gravity. So you end up with these kind of nodes, the densest regions, and then they kind of string together between the nodes, and that forms this web-like structure. Yeah.
All right. So I suggest let us thank Charlotte again.